awesome it caught on and other people started doing it?
Yes.
But you want to be different though.
Yeah, that's true. I actually like style and fashion. Like they're cool. Like it took me a long time to be able to admit that to myself because I think I grew up in a place that was really it had very distinct and strongly normative gender roles.
Okay.
And being like caring at all about style and fashion was like definitely not cool if you were a guy.
It's definitely not cool.
But like I was obsessed with shoes when I was a kid. Like I remember like I would walk around and like I might not even notice like what your face looked like, but I would see your shoes. Like I was looking, you know, I was really into like Nikes and Jordans and all that kind of stuff. So that was like I was like thinking about that all the time. But yeah, beyond that in the East Bay catalog, it was like I was confined.
Huge, you know?
But now I'm like I'm liberated. I can just do whatever I want with my fashion. I thought about some really good stuff. I've floated some ideas that Ashley has really not liked, but I haven't gone too far down that path yet. But we'll see.
I have a feeling after I graduate, I might start dressing like you.
Could get even more different.
If we were in the same
I've got some
stuff,
ideas, some good ideas. I think. I really like I'm not goth really in any way, and like I don't want to like appropriate that little subculture or anything, but I like goth style a lot.
Like some of the items they wear, or their whole style.
Just like the style, like the dark thing. I really like black, and
Me too.
yeah, like I could totally see myself adopting some of their style stuff.
Like big, huge boots with skinny jeans and stuff.
I mean, more like fashionably appropriate boots with skinny jeans, and then like I like the eyeshadow on guys and like all that stuff happening. It's pretty sweet. Yeah, it's cool. I like it. Yeah, I think that most of the time you feel like you can't do that unless you're in high school and you're emo, or you're in a band and you're emo. So.
You definitely have to look like you used to be in a band, though. Like.
Yeah. I try. Okay. So let's finish this problem that we were working on. Remember, it was not what to wear, but in fact it was what is the current through this inductor and the voltage across it as a function of time. So we had gotten pretty far. We had done steps 1, 2, 3, 4, 5, 6, A, B, C, I. Well, actually, this is back to 1, 2. They're Roman numerals. We gotten that far. So we haven't finished 2 yet. So the particular solution is what was next. Remember that we're solving the differential equation that we derived right here, right? Okay. First order. I mean, this is actually something that you guys did in your homework, so this is going to be like extra boring from here on out. But we'll do it anyways. Just for the look. So, what do we do with this particular solution that we wrote down? We assumed it was of this form, right? That it's got to be a sinusoid, and what we did was we said, oh, the input is a sine omega t. That means the form of the particular solution should be k1 sine omega t plus k2 sine, or cosine omega t.
You need to take the derivative with respect to time.
Yeah, and that's because we're going to plug it in and we're going to check to see, first of all, is it a solution? And we're going to check to see if it is a solution by plugging it into this differential equation and saying, are there any values of k1 and k2 that make this a solution? And if we can solve for a k1 and a k2, then the answer is yes. and we have ourselves a solution. And we also determined our coefficients along the way, because good job us. Okay, self 5. That's what that is. Okay, so let's plug it in. The first term to plug it into is tau di dt, right? So we got to take the time derivative. I'll pop our little tau out here on front, and then we're going to take, notice time derivative, sine omega t, cosine omega t, both have omega t in them. So chain rule, they're both going to have time derivative of omega t, which is omega, which we're going to multiply out front. So let's just factor it out right away, because we like doing multiple steps at once, because we don't like to write a lot. Writing a lot is not fun. So tau omega times k1, which is a constant, sine omega t. What's the time derivative of that? Cosine omega t. And we already did the chain rule omega t and the omega we pulled out. And then derivative of cosine omega t is negative sine omega t, and then times omega, but we pulled the omega out already. So that's the first term of the differential equation. Check. All right. The second term is just plus IL, right? So just plus K1 sine omega t plus K2 cosine omega t. All of that is equal to whatever the input is, right? IS, which we determined is A sine omega t from the problem statement. So A sine omega t. Okay. Now, this is a nonlinear relationship, and it actually gives us two linear relationships from it. Because on the left-hand side, all of the cosine terms have to be equal to all of the cosine terms on the right-hand side. Similarly, with the sine terms on the left-hand side, they have to be equal to all of the sine terms on the right-hand side. So the cosine terms here have a coefficient of 0 on the right-hand side, right? We're going to use that. So let's write an algebraic expression for the cosine terms first. So the first cosine term we have is tau omega k1 from there, cosine. The second cosine is k2 from there, right? Plus k2 equals the cosine coefficient on the right-hand side is 0. And then with the sine terms, we have negative tau omega k2 for the sine. And then for this sine is a k1 plus k1 equals, on the right-hand side, we have a, right? A. Right. So we have two linear equations and two unknowns, k1 and k2. Pretty sure we can solve that. We know how. We have the skills. So those two, let's take it to the next line. I'll solve this one for k2. It's easily solved for k2 equals negative tau omega k1, right? Let's just plug this in for k2 in this expression, leaving us with eliminating k2 from that one and giving us that negative, well, so negative tau omega times negative tau omega is going to be tau omega squared times, there's still a k1, plus k1 equals a. Okay. Now we're getting close. We can factor out K1 and divide what's left over on both sides. We get A divided by tau omega. Tau omega squared plus 1. Wow. So that's K1. Take that, plug it in to this expression for K2, which gives K2 equals, very similar expression, negative A tau omega divided by tau omega squared plus 1. Holy algebra, right? But, you know, our familiar algebraic steps, right? Just solving the system of two linear equations for two unknowns. So K1 and K2 are determined, which means that our particular solution can be written with these terms plugged in now. So let's do that. ILP of t. We'll plug K1 and K2, and notice that they're mostly the same, right? So let's just factor out the sameness. That is the technical way of describing it. Factoring out the sameness. And what's left inside is so K1, so sine omega t, because factored out all of K1. And then K2, we factored out most of it, but what's left is negative tau omega cosine omega t. So that's that. Okay. Good. So let's write so this is like, that was the end of our particular solution. We got it, right? So let's find the total or general solution, right? Total solution is that IL of t is equal to the homogeneous part, which we solved for last time, plus the particular part, which we just solved for. I know you guys knew that. I just thought it was important to repeat in case somebody watching the video, not somebody here, who was definitely paying attention, wasn't paying attention. Okay, so IL of t is equal to homogeneous solution, scroll, 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 it's just kappa e to the minus t over tau, right? Kappa e to the minus t over tau. Plus the homogeneous, which, plus the particular, which we just wrote. So let's, and this is just K1. I'm gonna just call this K1 now, because I don't want to keep rewriting it. This term right here, it was our solution for K1. I just don't want to keep writing it because it's big, right? It's big and it's Friday. So we're just going to call it K1 still. Even though we know that that's solved for, we just don't want to keep rewriting it. Times sine omega t minus tau omega cosine omega t. Good. So that's our total solution. And notice that, so everything in this second term is determined, right? All the K1 is a known quantity. Determined those coefficients, right? But kappa we never determined. So kappa is still sort of on the table as far as open problem. So step 4 is, of course, to plug in the initial condition and find the specific solution. Okay. So we apply the initial condition. Initial condition is that, stated in the problem, IL at time equals 0 is equal to some constant I0. Okay? So let's say I0, that constant, is equal to whatever this is when time is equal to 0, right? So kappa e to the 0, which is just 1, plus this thing, which is k1. What is sine of 0? 0. So 0 minus tau omega times cosine of 0, which is 1. Excellent. So what we're trying to solve for here, I know it might be confusing. What's the unknown? I don't know. They're all just symbols. We gotta keep track, right? Keep track of what's known. So I0 is given. It's the initial condition. K1 we solve for. Tau and omega. So tau we defined ourselves. Omega is given in the problem. It's whatever the input frequency is. So we're trying to solve for kappa here. That's our goal. If we had a second order system, we would have kappa 1 and kappa 2 to solve for. So we'd have like a 2 solution situation like up there. But we only have one because first order. And that gives us a kappa equals what?
K1 times 0.
It's I0 plus,
I just was gonna put that last.
yeah, K1 tau omega, right? Yeah. So that's it. Not too bad. Also, really helpful once you solve for a constant, not to keep rewriting everything in the constant. I feel like half of people's problem on these things is that they like get tired of writing. So this is one way to help, is to not rewrite everything over and over again. Okay. Good. So we have our specific solution now because we have kappa solved for. So we can rewrite it, but really it's just going to be rewriting the thing from above. IL of t is equal to kappa, which is now a known thing, but we don't want to rewrite again because why would we? E to the minus t over tau plus k1 sine omega t minus tau omega cosine omega t. Now, I will say that once you get to the end like this, generally it's good to just plug everything back in, because sometimes there's like some simplifying process that can take place. Like maybe if you plug in K1 and you plug in kappa, you find, oh, there's like a common term and you can factor it out or something like that. So it's good to do. In this case, there's really not anything that can simplify, so we don't really need to. Okay. But the one thing that I do want to do is I want to rewrite this term in terms of a single sinusoid. Okay? And then it'll help us interpret what the solution is. Because we got the solution, we want to interpret it, but it's a little weird to have these two sinusoids. They're at the same frequency, right? And there's not an offset between them. So actually, when you have a sine of a quantity and the cosine of the same quantity that are added together in some way, added or subtracted, you can combine them into a single sinusoid. I don't know what the name of these is, but I call them the 2-to-1 formulas. But if you go to the website, class website, and then you go to the electronics, whatever these are, notes and stuff, you'll find that, oh, now I have this nice trigonometry reference. Okay. Check that out. These are just, trig identities that I like to keep around just in case something like this comes up. And we want to know, how do you combine this into a single sinusoid? So A dot 14, in its different letters, tells you how to do that. So this is what we have, right? A sine u plus B cosine u. We can combine them to be a sine or a cosine. We're going to choose sine because our input was a sine. If our input was cosine, it would make sense to do cosine. But technically you could do a cosine if you wanted. So we'll do sine. So all we need to do is compute C and compute phi. Okay, so C is just the square root of the sum of the squares of the two coefficients, and phi is the arctangent of the cosine term's coefficient divided by the sine term's coefficient. So you can just use that formula straight up. I'm not going to try to prove that. Just dropped from the sky, and we're going to apply it. Okay? So let's, shouldn't probably use C because capacitors, but that formula uses C, so I'm going to use it. I'm going to say, let's compute what C is. That's the square root of, well, actually, yeah, okay, we'll do it. Notice there's a K1 that shows up in both A and B, right? And so you can factor it out. Well, I'll stick it in. Maybe you guys will feel more comfortable that way. Okay, K1 times 1, right? Squared. Plus K1 times negative tau omega. So I'll put the negative sign before the K. Negative K1 tau omega squared. So that's our C, and if we wanted to, we could factor out a K1 squared, and then, we can hit it with the square root. So we end up with absolute value of K1, which we probably should write it as absolute value, but assuming A is positive, this is always going to be positive. And so we probably should be explicit about assuming A is positive, blah, 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 but we're going to instead just skip right to K1 and assume that we're not being stupid and I shouldn't say stupid, forgetful, and plugging in a negative number for A, that would be violating this. So K1 times what's left over? 1 plus tau omega squared. Okay, so that's our C. Our phi is the arctangent of the cosine component divided by the sine component. Cosine component is negative tau omega K1. The sine component is K1. So this is equal to, the K1s cancel. Actually, it's an odd function, the arctangent, so you can pull out the negative sign. Arctangent of tau omega. And that's our phi. So therefore, is everybody done writing that? Sorry, I realize I go kind of fast when I write. It's part of why I have these notes where a lot of it's already there. Otherwise, people are like, wait. That's how people sound to me. This is my first cup of coffee this morning, and it was like so needed. I went over and I tried to get it from the Monk's Bean earlier. They were out. I was sitting there like, and there was like 2 drips, but I still drank the 2 drips because I needed it. And then I was like, okay, when are you gonna have it? So I came back 15 minutes later. And then I had bought, the chemistry's having a bake sale over there, so I ended up buying stuff I shouldn't have eaten.
What are they doing besides?
I don't know, but they're good at that. Let me tell you. Those almond tart things, legit. And then they had these like, I thought they were just like parfaits, and I was like, nah, parfait. But then it was like it's like some sort of shortcake. I'm like, I could get into that. So I asked, and they don't close till 2. So after lunch, probably gonna have another thing.
I said another.
So
You know, you had the-
yeah, I had the almond tart. Definitely did. So we can combine this. This is all of the C and the phi thing was just to combine these into one sinusoid. So let's do that. Our IL of t is now equal to, we still have our kappa e to the minus t over ta plus, and now instead of having all of this weirdness with the K1 and the blah blah, all we have is C times sine of omega t plus phi, where kappa and C and phi have been defined above in terms of known quantities. All right, so that's good. What are we looking at then? Like, what is this strange object? Yeah, so it's the current going through the inductor as a function of time. And when we look at this and we say, okay, there's this first component. There are clearly two terms, right? There's this term and then there's this term. So this exponentially decaying term is going to go away once time gets very big, right? Because as time gets larger, e to the minus whatever is going to go to 0 exponentially, and then it'll be gone. And then what's going to be left over is this sinusoidal term, which, let's look at it for a minute. The sinusoidal term has the same frequency as the input, okay? And this is kind of like a big deal. So when we're going to keep harping on this, but whenever you input a sine wave at a certain frequency, the steady state response is also going to have a sine wave at that frequency. As long as the system is linear, nonlinear systems, all bets are off. But for a linear system, if you put in a sinusoid, you get out a sinusoid at the same frequency. Okay, so that's cool. But what do we do? Or what's changed about it? So the sine wave went in, sine wave came out, same frequency. Its amplitude changed. Okay. Now it's C instead of A. It's a new letter, but also it stands for something else, right? And phi, it has a phase shift, right? So you get a sine wave output that has a different amplitude and a different phase, but that's the only thing that's different. Different amplitude and phase. That's like the joke about how you dated a girl who looked like Heidi Klum except shorter and the face was different. Yeah. Yeah, that's a stupid joke, I know, but I think it's funny. Okay, so yeah, but this is what we got, what we put in, but it looks a little bit different than the way we put it. Okay. So this is the end of that first part. IL. What's IL? We found IL. What is, and I'll put step 7 here because this is the next question, is what is VL? So there are a couple ways you can solve for VL. You can go back to our algebraic expressions here, armed with IL, and solve for VL. That's one way to go. The other way to go is to go directly to the elemental equation, right? The elemental equation is always going to relate the voltage and the current of that element, and so we have a direct relationship that we can go straight to. And I think in this case, this is the easier one. So VL is equal to L times DIL dt. So we have to take a derivative and multiply it by L. But otherwise, we've got it, right? So from the elemental equation, we have that VL equals L DIL dt. So that's L times, what is the time derivative of this expression? So I'm gonna distribute the L. So I'm gonna just have to remember when I write the second term to say the L again. See how it goes. Say again. What's the derivative of this?
Oh,
Yeah, so a negative 1 over tau comes out front, and then it's the same thing, because it's just chain rule, because derivative e to the x is e to the x, but then you got chain rule of x, which in this case is negative t over tau. So we end up with a negative L times kappa, well, I'll put them both up there. So fraction negative L kappa divided by tau, e to the minus t over tau. So at this point, I mean, it might make sense to plug in kappa and see if something cancels, because, you know, we've got a couple other things multiplying it. But I don't think anything really does, so not great. So then this other term, so derivative of, well, so this is a constant c. So derivative of sine, cosine. Chain rule, there's an omega, so we get L, C, omega, cosine, omega t plus phi. So there you go. That's the voltage. I feel like this is really like one of your homeworks, right?
yeah.
So you can kind of see like the common elements here. Even though I think your homework problem is dealing with voltage and not current source, and it's dealing with a different looking setup, it's still a first order system with a sinusoidal input, and they all kind of look the same. So this is what's going to happen. Okay, great. Any questions on that? Because what I want to do, if there aren't, and even if there are, is move on to the next lecture, and we're gonna, in the next lecture, we're gonna plot this, and do further interpretation of it. Any questions on it though before we move on?
Do you want us to rewrite it in terms of one sinusoid or?
I think it depends on the situation. I don't want to make a blanket statement. So I would say the world is not an exam, right? So like in the real world, when you do this, you'd want to, right?
Okay.
On an exam, like, do you need to take the time to do it? It just depends on the question that I ask. Like, if I ask you for, like, what's the phase shift, like, you're going to have to compute it anyway. So, but if I just say, what's the solution, then you don't necessarily have, unless I say, write it in terms of a single sine, cosine. Just look at, like, the context and what's asked. But typically, we do it just because it's easier to interpret. And in general, it's just a good idea to simplify things down. All right. Very good. Anything else?